Hello everyone. Today let's solve the problem number 1584. So min cost to connect all the points. So what the question states here, we are given a set of points. You can clearly see here they have shown in the graph. So we have the x and y coordinates here. We are given a set of points on a 2D plane, and we need to connect all points with the minimum possible cost. So what we need to do here, we need to connect all the points with the minimum possible cost. That's what we need to do. This one we have to keep in mind. We are given a set of points on the 2D plane, and we need to connect all the points with the minimum possible cost. So the cost to connect 2 points is defined by the Manhattan distance. So this, I hope this is clear. The cost to connect point is defined by the Manhattan distance. The formula they have given here: xi minus xj mod of xi minus xj plus mod of yi minus yj. So here, by looking at the mod, we know that every time we get the value positive itself, right? So mod of xi minus xj plus mod of yi minus yj. So the cost to connect 2 points. So the cost to connect to the 2 points is defined by the Manhattan distance. So now we know the formula: xi minus xj mod of xi minus xj plus mod of yi minus yj. So this one, let's keep this in mind. So we have to connect all the points with minimum possible cost, one thing, and the cost to connect 2 points is defined by the Manhattan distance. So xi minus xj plus y minus yj. These two things we have to keep in mind, and we must also ensure that all the points are connected. Means here all the points should be connected at any cost, meaning there should be exactly one unique path between every pair of points. So all the points should be connected at any cost, meaning there should be exactly one unique path between every pair of points. So here we have to connect every node. In case of graph, if we represent that, we have to every node must be connected, right? All the points or all the nodes has to be connected in that case. That's what they are saying here. Means there should be exactly one unique path between every pair of points. So I hope this is clear. First thing we need to consider here is we need to connect all the points with the minimum possible cost, and the cost between 2 points is calculated by the Manhattan distance, by this one, mod of xi minus xj plus yi minus yj. And third thing is we have to ensure that all the points are connected. Means we should have one unique path between every pair of points. These three things we have to keep in mind. I hope the question is completely clear. See here, they have given here points. See, x and y coordinates we have. This is 0, 0. This one they have mentioned. Just give me a second here. Here 0, 0 they have mentioned here. 2, 2, this one, and 3, 10, 5, 2, and 7, 0. So the minimum, this one, we have to calculate the we need to connect all points with the minimum possible cost, right? So here they have, in the second graph, or in the second graph, they have shown that itself here. So here you can clearly see the minimum possible cost graph they have shown here. So the output that we need to get here is this one, 20. So by looking at the problem itself, we can say this is minimum spanning tree question, right? So here you can clearly see cost. Initially they have calculated here this one. Just give me a second here. This one, cost 4 they have given here. This one, between this one and this one. So this one they have calculated by the formula xi minus xj plus yi minus yj, mod of xi minus xj plus yi minus yj. This one will be 3, 9, and 4. So while we sum up all the things, suppose 4, 3, 9, and 4, we will get the output 20. So how we can yield to this graph? So this one. So how can we calculate the minimum spanning tree or minimum distance? So a minimum possible cost. How can we yield to this one? So that we will see in the approach, right? So I hope the question is completely clear. Let's initially discuss the approach, followed by this one, edge cases one by one, and then finally write the code and discuss the complexities of the code that we have written. Initially, as usual, let's discuss the approach. I'll just consider the example 1 they have mentioned in the question. I'll just take the example 1 so that you can try the same thing for the example 2 for the approach. So I'll just be considering example 1. So let's discuss the approach step by step. First thing that we have to keep in mind here is we will be making use of Prim's algorithm with the minimum priority queue. Again, I'm telling, just keep this in mind. Prim's algorithm with minimum priority queue. If we have discussed many algorithms. So I have mentioned some important algorithms. I have different playlist for that. You can just go through some important algorithms. So when we are solving the graph problems, it will be easier for us to understand, right? So here in this case, we'll be going with the Prim's algorithm with minimum priority queue. Just keep this in mind. So I have just considered the same first example that they have given in the question, right? Same thing. So let's discuss this one. So what we have to find out here, we have to find out the minimum possible cost, right? So we need to connect all the points with the minimum possible cost. So we have different ways of connecting the edges to different points, right? Suppose if we consider this one, we'll be going with the formula xi minus xj plus yi minus yj. So this one, 2 minus 0, 2 minus 0. 2 plus 2 will be 4 here for this edge. Next, if we consider this one, so we consider this one to this one. Now we are considering this one to this one here. First we consider this one. Now let's consider this one. This will be 3 minus 2, 1, and 10 minus 2 will be 8. 1 plus 8 will be 9. So mod of xi minus xj, every time we'll be getting the positive value itself. We don't have to care about the negative and the positive. So we just have to calculate, that's it. So here next we will consider this one. So just give me a second. This one. So here it will be 5 minus 3 nothing but 2. 2 minus 10 nothing but 8. 2 plus 8 will be here 10 in this case. So next we'll be calculating this one. 0 minus 2 will be 7 minus 5 will be 2 in this case. 2 0 minus 2. 2 plus 2 will be 4 here in this case. Finally we'll calculate this one. 7 minus 0 7. 7 plus 0 will be 7 itself. So we are adding everything now. 4 plus 9 plus 10 plus 7, 0, 10 plus 4 plus 7. So this will be 19, 23, 23 plus 4, 27, 27 plus 7 here will lead us to 34. So this will give us the possible, the total cost this is giving here is 34 in this case. But they have given in the output, if you have observed in the question, they have given us the graph where it has led to the minimum cost 20, right? How can we calculate that? This is one of the way. This fails here. I just wanted to show this is one of the way we can connect the different edges to the points, right? Here every edge is clear. So we are connecting every edge. We are making use of every point. Sorry, we are making use of every points here, right? So this is one of the way. But total cost here we are getting is 34. This fails actually, right? So we have to go with the minimum. We have to find out the minimum possible cost, right? So we have to connect all the points with the minimum possible cost. That let's see that itself how can we calculate. So let's come to the minimum cost graph that they have given in the question, right? In this case they have shown this one, right? So let's go with the formula here. 2 minus 0 here in this case, 2 minus 0, 2 minus 0 plus 2 plus 2 will be 4. So in this case, so we have calculated this one. This one we have already calculated in the previous one. So I'll just consider this one itself. Yeah, 9 it is, right? So let me give here 9. So here we are considering this one now, right? This one will be 5 minus 2, 3. 3 minus 0. 3 plus 0 will be 3 here in this case. So next let's consider this one. Here this will be 7 minus 5, 2. 2 minus 0, 2. So this one will be 2 plus 2. This will be 4. So this is the minimum possible cost that they have given here. So when we calculate here, 4 plus 9 plus 3 plus 4 in this case. So we will be getting 9 plus 4, 13. 13 plus 3, 16. 16 plus 4, 20. So this is the graph that they have shown. So how can we yield to this graph? So how can we calculate this one? What will be the approach? Let's see the same thing here. So first thing, we'll be going with the Prim's algorithm here. Prim's algorithm execution. Let's see the same thing with the minimum priority queue. First, what we will do, we will go with, we can start with any point. In case of we are making use of the minimum priority queue. When we are making use of the minimum priority queue, just give me a second here. Did I miss something here? Right. So first what we will do, we will go with the point 0, 0. This one. We will start with this one. We'll be making use of the min heap, nothing but min priority queue. To always pick the smallest edge. So to always pick the smallest edge, first we are starting from 0, 0, right? To always pick the smallest edge, we will be considering minimum priority queue. I hope this is clear why we are making use of the minimum priority queue. So this will be handy, right? Minimum min priority queue. So we can go with the min heap as well. But while writing the code, we have to build the min heap from scratch. Leetcode doesn't provide built-in this one min heap. So we have to build the min heap, and we have to include that one in the main function, right? That will be lengthier. Let's go with the min priority queue, right? So in this case, we'll be making use of the min priority queue. Then what we will do, first step was we'll start from the smallest edge, because we'll be making use of the min priority queue to always pick the smallest edge. Next thing is, we will mark the visited nodes to avoid cycles. Once we start with this one, we will mark this one as visited to avoid the cycles. And finally, we will add all the edges of unvisited nodes to the heap. Suppose if we are starting from here, so initialization is 0, 0. These edges are unvisited initially, right? So all the edges, we will add that one to the priority queue. That's what we will be doing here. So next step we need to keep in mind here is, we have to construct the minimum spanning tree step by step. Again, I'm telling, we will be constructing the minimum spanning tree, or we will now construct the minimum spanning tree, MST, step by step. So graph representation, we have already got the idea. So the failed one we have seen here, and the one we have to get here, 20 as the minimum possible cost, right? So that's what we need to find out. So one thing, we know the formula also, this one, to calculate the MST between 2 points, nothing but mod of xi minus xj plus mod of yi minus yj. We know the formula as well. Let's move to the main step, right? So I'll just come here. First, we will be starting from 0, 0, because we'll be considering smallest edge, right? So we have went with the minimum priority queue. We will always get the smallest edge, right? So this we know. We'll start from 0, 0. So first we have 0, 0 to 2, 2, 0, 0 to this one 3, 10, 0, 0 to this one 5, 2 and 7, 0. 4 possible points we have. So let's apply the Manhattan distance here. Manhattan distance calculation here. It will be 0 minus 2 plus 0 minus 2, right? Mod this one will get 2 plus 2, nothing but 4. So this will be 0 minus 3 plus 0 minus 10 here. In this case, we will get 13. This will be 0 minus 5 plus 0 minus 2. This will lead us to 7, right? This will be 0 minus 7 xi minus xj means this one xi minus xj yi minus yj. So 0 minus 7 xi minus this one, sorry, 0 minus 7 plus 0 minus 0. Every time we are doing the same thing here. This will give us 7. So every time we are considering the minimum cost edge. Minimum cost edge here is 4. The value, the least value we are considering. Minimum cost here we can clearly see this is from 0, 0 to 2, 2. So the total cost here will be 4. This leads us to 4. Possible cost is 4 here, right, in this case. So from step 1 we got the total cost 4 here, you can clearly see. Let's move on with the second step. We have already considered here, in this case we have already considered the 0, 0. Let's ignore the 0, 0. Let's move on with the, let's start with the 2, 2 in the second step. So here we have to consider this one 3, 10, 2, 2 to 3, 10, 2, 2 to this one 5, 2 and 2, 2 to 7, 0. These 3 points are left here. So let's go with here 2, 2 to 3, 10. So let's calculate this one using the Manhattan distance calculation. This will be 0 minus 2 plus 0 minus 2. So this will be again 4. Sorry, not this one. We are doing this one, right? Sorry, I completely forgot. Just give me a second here. This one will be, sorry, 2 minus 3 here plus 2 minus 10. So this is fine. This will give us 9. So this will be 2 minus 5 plus 2 minus 2 here. This will give us 3. So here this will be 2 minus 7 plus 2 minus 0. This is nothing but 5 plus 2 here. This will be 7. So here minimum cost edge that we have to consider here is 3, because we have the minimum value 3 here from 2, 2 to 5, 2 here. So this will be 3. This gives us basically 3, right? So the total cost will be here now. So the total cost will be here this one plus previous one. So here 3 plus 4 total cost for the first step was 4. This will be 3 plus 4, nothing but 7. Now the total cost we have here is 7, right? So this is fine. This is for the step 2. So we were moving to the 2, 2. Next we have to consider this one. Let me come to the graph. So now we are ignoring 0, 0 and 2, 2. Let's consider this one 5, 2 we need to consider, right? Sorry, this one 5, 2, because we have the smallest edge from 2, 2 to 5, 2, right? Here you can clearly see. So just give me a second here. Yeah, 2, 2 to 5, 2. We have to consider 5, 2 here. So I'll just come here. So 5, 2. Now we have already considered 2, 2 and 0, 0. 5, 2 to 3, 10 we need to consider this edge, this one, and 5, 2 to 7, 0. These two edges are like they are considering these two. So I'll just come here. So yeah, 5, 2. We have current minimum spanning tree here we have is 0, 0, 2, 2, and we have moved to the 5, 2 here, because the last time the edge, minimum cost edge was 2, 2 to 5, 2, that yield to the 3 possible cost 3, right? So this one we are considering here 0, 0, 2, 2 and 5, 2 here. So this one, let's calculate the Manhattan distance quickly. So here in this case it will be 5 minus 3 plus 2 minus 10. This will be 10, and this one will be 5 minus 7 plus 2 minus 0. Here in this case it will be 2. So minimum cost edge will be here in this case 5, 2. This one we need to consider small value. So this is from 5, 2 to 7, 0 and with the value of 2. So the total cost will be here now 2 plus previous one what we got 7. 2 plus 7 will be 9 here. So the total cost will be 9 in this case, right? I hope this is clear. So next let's move on to the this one. We have the edge minimum cost edge now 5, 2 to 7, 0. Now we have already considered 0, 0, 2, 2, 5, 2. Now we will be considering 7, 0 and we have only one edge left, that is nothing but 2, 3, 10. We have already made use of 0, 0, 2, 2, 5, 2. So we have two edges. This was the minimum spanning edge that we need to consider, that L to the this one minimum possible cost. So we'll be considering 7, 0 and 7, 0 we have only one edge left, that is nothing but 3, 10 that we need to calculate right here. So in the current minimum spanning tree we are having 0, 0, 2, 2, 5, 2 and in this step we'll be adding 7, 0. We are moving to 7, 0 here, right? Let's quickly calculate the Manhattan distance. So this will be 7 minus 0 plus this one mod of 0 minus 10 here in this case. Sorry, did I miss anything? 3, 10 we have right here. Yeah, 0 minus 10. This is fine. So in this case we have 7 minus 3 and 0 minus 10. This will be so yeah, this has to be 7 minus 3, not 7 minus 0. Xi minus xj, yi minus yj, right? 7 minus 3. This will be 4 plus 10 right here in this case. 4 plus 10, this will be 4 plus this one 10 we got here. Give me a second here. So here it has to be 4 plus 10, 14, not 11. This is fine. This one here when we come, I have done one mistake in the previous step basically. So here 5 minus 7, 2. 2 plus 2 here, it has to be 4, not 2 here. So this one, the value has to be 4. We have to do 4 plus 7. In this case, we'll get the output 11, not 9 in the step 3. So here now we have 14. So the total cost, minimum cost edge here should be from 7, 0 to 3, 10. This has to be 14, right? The value we got is 14. So previous one was 11. But here when we do 14 plus 11, the total cost has to be 25. But we have to get the output 20. So in this case, we are not considering 14. Minimum cost edge here is not from 7, 0 to 3, 10. We will ignore this one. You can see here one thing in this diagram. We already have the minimum value 9 from 2, 2 to 3, 10. So the value 9 and 14 we have. Also from 5, 2 to 3, 10 we have the value 10. So from 2, 2 to 3, 10 and this one 5, 2 to 3, 10 and 7, 0 to 3, 10 we have the least value 9. Least possible cost here would be 9. That we will be considering in this case. So the minimum cost edge we will be considering here for the 3, 10 we already have 9 in this case accordingly with the this one Prim's algorithm. So from this one we will be considering from 2, 2 to 3, 10 here in this case. So this will be 9, not 14. So the total cost would be here 9 plus previous one. Previous one it was 11. So 9 plus 11 here would be 20 in this case. So don't get confused here. We will get the output 14. So 14 plus 11 will lead to output 25. So 25 here will be here will not be considering the 14. Instead, we will be considering the least least cost to 3 comma 10, because we already have the value 9, 14 and 10 from 2 comma 2 this one, from 2 comma 2, 5 comma 2 and 7 comma 0. We will be considering the least value from them. So then it will be here in this case 9 plus 11 will be considering 9, and it will be 9 plus 11 will be 20. So the final minimum cost that we got here is 20 accordingly with the Prim's algorithm. I hope this is completely clear. Again, I am telling in the last in the step 4, so from 2 comma 2 to 3 comma 10 we had the possible cost 9, and from 5 comma 2 to 3 comma 10 we had 10, and this one from 7 comma 0 to 3 comma 10 we had value 14. So out of which accordingly with the Prim's algorithm we will be considering the least value. So since we are always picking the minimum costed, the algorithm already recorded that 3 comma 10 was reachable from 9, that is from 2 comma 2. So we used 9 instead of this one 14. So 9 plus 11 will give us the output 20. So don't get confused with this, right? So I hope this is clear. Don't get confused in the last step, right? So I hope this is the approach that we'll be going with. I hope the approach is completely clear. Let's quickly discuss the edge cases one by one. So first edge case I'll be going with single point. So let's quickly discuss all the edge cases. Single point input I'll be considering here 0 comma 0. So output will be 0 here. Why? Because we don't need any edges at all, right? We have the single point. So output will be 0 in this case. So second edge case, let's go with all points in a straight line. So we'll be considering all the points in straight line. So input I'll just consider here. All the points has to be in the straight line, right? So x will be 0. X coordinate. So xi will be 0 at this one here. This one will be 0 again. 0 comma 2. Let's consider any one value. 0 I have considered. It will be 0 throughout the input 0 comma 5 and 0 comma 10, because all points should be in the straight line, right? So output will be sum of consecutive Manhattan distance. You can just try out in the same way. If you want the output, you can just try out in the same way that I had showed for the example 1 in the approach, right? Sum of consecutive, this one Manhattan distance, I'll just give here MD. So this is for the condition all points in a straight line. Let's move on with the final edge case or the third edge case, large coordinates. I'll just give here large coordinates. This is for the condition large coordinates. In this case, input let me consider here 10 to the power of 6 or 10 to the power of 6. Accordingly with the constraints we are considering minus 10 to the power of 6 and minus 10 to the power of 6. This is fine. And finally, let's consider here some 0 comma 0. I will just consider. So here we have to test the efficiency when handling the large cases. So let's not so I'll not be writing any output here. This is just to show that we have to it has to handle the large coordinates accordingly with the constraint they have given. So I just consider 10 to the power of 6 and negative minus 10 to the power of 6 here. So this is fine. First we considered for the single point. First edge case was for the single point. Second edge case was for the all points in a straight line, and third edge case was for large coordinates. So I hope all the edge cases are clear. Now let's start writing the code. So first let's make use of the variable in, because we have to store the number of points given in the input array. So I'll just come here with n equals, this is nothing but the points they have given right here, length of the points. So this is fine. Next step is I'll just make use of the result variable because we have to store the final minimum cost. That's what they have asked in the question, right? That is required to connect all the points. So initially, let me consider here result and initialize the result to 0. So I hope this is clear. Also, we have to go with the, we are going with the minimum priority queue. So let me make use of the variable PQ. Also, where each element in the array, cost and index will be considering, right? Yeah. Uh, so here what we are doing, we are going with the minimum priority queue, where each element is an array, nothing but cost comma index, right? I'll just give here, let PQ equals, let's create the min priority queue here. Min priority queue. Let's assign the priority x, this one, x0. The first element has to be the smallest element every time here. So we are picking the smallest index every time, if you remember, right? In the approach that we saw that, right? So that is the reason priority I am setting to x of 0. First element has to be the smallest one. So this is fine, I think. I hope this is clear. The next step is we are making use of the visited variable here because and we are making use of the hash set here. Nothing but visited variable. We are making use of the hash set because set keeps track of the points that are already added to the this one minimum spanning tree. So after visiting particular node, we have to mark that one as visited, right? In that case, set will help us track of the points that are already added to the minimum spanning tree. So I'll just give here visited. Sorry, yeah, visited. Let me set this one to the new set. So this is fine. The next step is, let's start with the this one index 0. Nothing but we are starting with the point index 0 and we will push that one to the priority queue with the cost 0 initialization part, right? So let's go with the enqueue as we are making use of the priority queue. So I'll just give you variable PQ we have mentioned here, right? So let me go here itself, PQ, or let me do one thing, Q dot enqueue of initially cost. Let's set this one to the 0, 0 within the array. So we are starting with the index 0 and also we are pushing it to the priority queue with the cost 0, index 0 and the cost 0. That's what we are doing here. I hope this is clear. Next step is we have to let's go with the simple while loop here. Well, visited, it says greater than n. Then what we have to do, we have to continue until all the points are connected. So when visited points equals n, right, we have to continue until all the points are connected to n. So this has to be while visited size less than n, then we have to proceed further until, or we have to continue until all the points are connected. That is the reason we are going with the while loop. So next step is, let's extract the minimum cost edge from the priority queue. So here this will be let cost comma point PQ NQ element. I hope this is clear. After extracting the minimum cost edge from the priority queue, what we have to do, if the current point is already visited, then we will skip it and continue. Means if the current point, we are making use of the set for that purpose itself, right? If the current point is already visited, then we have to skip that one and we will continue in the fourth, this one, step 4. So while we were calculating the Manhattan distance, we already had the cost 9 and 14 from this one 2 comma 2 and 5 comma this one 7 comma 0, 5 comma 2 and 7 comma 0. So previously we had 9 and 10 already, so we got the output 14. We just considered this one 9 instead of 14 because we already have the minimum value 9. So we got 9 plus 11, finally we got 20 as this one minimum cost edge, final this one final cost, total cost as output we got 20, right? So that is how we got. So here, if the current point is already visited, we will skip it and continue. I'll just write a simple if condition here in this case. Visited has of point. If we already has have the point, then I'll just make use of the continue keyword here. We will skip this one, right? So I'm just making use of the continue in this case. So, and also we have to mark the current point as visited. Let's make use of add property of the set, and I'll just give you a point. So we are just marking this one as visited. So next step after marking this one point as visited, we have to add the cost of the edge to the final result as well. So in this case, result I have considered result equals result plus cost. I just keep articulate in this way in the form of code in this way. So next step, if the point is not visited, then we have to calculate its connection cost, right? We'll be making use of the this one Manhattan distance formula, and if the point is not visited at all, we have to calculate its connection cost. So for all the points we have to write. So let's make use of the iteration here. Let I equals 0, I less than n. So here then let's increment the I. So if the point is not visited, then we have to calculate its connection cost. So not of visited means visited dot has of iterated value. So here let's calculate the connection cost. So here formula is, I'll just give here less this distance equals, we have the negative value, we have to go with mod of xi minus xj plus yi minus myj. So I'll just make use of the absolute here, mat dot abs in this case, points, point, this is fine, 0 minus points I 0. This is fine. This is for the x coordinate. Then we have to write for the y coordinates as well. So I'll just copy the same thing, or let me type this one quickly. Mat dot absolute of this one, same point and 1, this is fine, minus points of I 1. This is fine. This is the formula that we'll be going with. We are just calculating the Manhattan distance between the current point and the unvisited point, right? So the next step here is we have to push the new edge. So the new edge that we got here, nothing but cost comma point in the we will get in this form, right? Cost comma point within the array. So we are pushing the new edge into the priority queue. Again, we'll be making use of NQ for this one. NQ distance comma I. So this one has to be within the array, right? So I forgot here. Let me add this one. Array. So this is fine. So this is it, right? Finally, we have to return the minimum cost that is required to connect all the points. In this case, we have considered. We are storing it on the result, right? So I'll just return result. This is fine. Let me format the code once and let me hit the run button. I hope this works. Let's see. So we have runtime error here. X of 0 cannot read properties of undefined 0 30. So what is wrong here? First element we are getting here, right? X of 0 would be fine. So let's check what we have done wrong here. So what mistake I have done here is in the line number 10. So what we are doing here, if the size of the visited is less than n, it has to be less than n, right? So we have to continue until all the points are connected. Means size of the visited has to be equal to n. Until that one we are continuing. So here in this case, in the line number 10, we have to extract the minimum cost edge from the priority queue. Means we have to get the this one minimum cost. In this case, we have to make use of the DQ, removing. So instead I had made use of the NQ. That was wrong. This is one thing. And in the line number 16, you can clearly see here, I have misspelled the word visited. It has become visited. So I'll just remove S here. I hope this works now. Let me hit the this one, run button. So you can clearly see here, now the sample test cases are getting passed. Let me hit the submit button very quickly. So you can clearly see here, all the test cases are getting passed. So the code works absolutely correct in this case, right? So let's quickly discuss the complexities of the code that we have written. So here, the approach that we went with here is Prince algorithm with minimum priority queue, that we know, right? So what would be the overall time complexity here? The overall time complexity would be here big O of n square log n, right? Why it is big of n square log n? Because we are iterating over all the points. So we are iterating over all the points, right? And we are also making use of the min heap. We are iterating over all the points, which leads us to the, and we are making use of the Prince algorithm, which leads us to big of n square. And we are making use of the minimum priority queue for the efficient edge selection every time. So minimum priority queue, it will be big of log n, and as we are iterating over all the edges, so it will be big of n square. Overall time complexity would be big of n square log n. So I'll just key here n to the power of 2, nothing but n square log n. So what would be the overall space complexity here? The overall space complexity would be big O of n to the power of 2 or n square. Why it is big of n square here? In the worst case, we are storing all the edges in the priority queue. See, every time we are checking for the smallest edge, right, in the priority queue. So in the worst case, we have to store all the edges in the priority queue. That leads to the overall space complexity of n square, right, big of n square. I hope this is clear. So the time complexity would be big of n square log n, and the space complexity would be big of n square, right? I hope the solution that we have written is completely clear. For now, this is it. Thanks for watching, guys.